Welcome again to the webinar, the open webinar of Pilot 3 in the context of the project Imoco 4.e. I am Riccardo Masiero of Crit, and I'm glad to introduce you this webinar, speaking first a little bit about what is Imoco 4.e. Imoco 4.e is a European project done by 45 partners from 13 different countries that gathered together in order to realize artificial intelligence and digital twin solution for industrial equipment, especially cyber physical equipment with movement parts. And the idea of Imoco 4.e is to implement different technologies that can be showcased in various pilots, demonstration, and use cases. In particular, in this project, we have 5 different pilots, 4 different demonstrators, and 4 different use cases. And the difference among the 3 are the business model underneath them. And today we will focus on Pilot 3, that is a pilot that addressed the domain of the high-speed packaging machine. So the implementation of artificial intelligence, digital twin technologies, but in particular artificial intelligence, that we will see to the world of high-speed packaging machines. The Imoco 4.e technologies can be grouped in 10 different clusters of technologies, 5 of which relates to Pilot 3, and are those that here are depicted in green. All these developed technologies can be seen as a sort of catalog of hardware and software solution. And today, thanks to the presentation of Pilot 3, we will see some of them, how has been designed and implemented in these 5 categories. Hardware platform to control the processing of data and the transmission of data, algorithms for predictive maintenance and artificial intelligence in general, and tools for data management in the networks. But what is Pilot 3 about? Pilot 3 is about the use of the Imoco technology in the context of packaging machines. In particular, we have analyzed real-world packaging machines and defined an abstraction model in order to describe them according to the main part that may form them. And thanks to this model, we have been able to formalize easily and clearly the main objective of Pilot 3, that is the realization of a proof of concept that may allow to substitute the currently used Windows PC in the cabinet of the packaging machines to run AI algorithms in the perspective of guarantee a real-time performance of the solution and dedicated resources of the solution that with the current PC is not possible to do. The general machine reference models is also used in order to describe the overall process of the machine, and according to that, identify two main needs that are targeted by the application that has been considered in Pilot 3, and in particular a need of improving the machine monitoring and the need of improving the quality control of the overall process. And the application that has been considered in this scenario are respectively a blade degradation application in order to see if the blade works properly or it presents some issue, and the improvement of the current quality control process with an application that focus on the check of the bottles in order to automatize the identification of bottles that are not formed correctly and must be considered as rust. So this is two screens that show you the final results in the blade degradation monitoring application and in the bottle check domain. I did the introduction of the webinar, then it's time to leave the floor to the people that actually realize the different technologies that allow to reach the application solutions. And we will start from the physical layer with the presentation of the real-time smart control platform by Fabienne of Unimore, and that contains the TSN platform based on FPGA that will be presented by Daniel from Sochi, and the Huawei Atlas 500 Pro platform that will be presented by Lorenzo of Evidence Huawei. Then we will see how we set up the solution to transmit and archive data with GNT by Tassos, that will present also two algorithms, one in edge, one in fog environment for predictive maintenance. And other two algorithms will be presented respectively by Dario and Tarquil. Dario from University of Sassari, that will present algorithm for sensor anomaly detection, and Tarquil from Digital Twin Technology, that will present an algorithm for image anomaly detection. So I will leave now the floor to Fabienne in order to start with the real-time smart control platform.
Thanks, Ricardo. And we are also working on autonomous systems. We have, for example, 5 autonomous driving cars, laser gate vehicles, delivery bots, some drones. We are also involved in autonomous racing, like in the Autonomous Challenge of F1 on 10. And we are around 70 researchers for a funding of 10 million euros. In Imoco 4.e, we are the leader of the building block 4, real-time smart control platform. And our objective is to provide technological solution aiming to enhance compute-intensive workloads at the edge using virtualization for performance and real-time guarantees. To do so, we bring in Imoco 4.e our expertise in real-time system deployment, our capacity to develop our virtualization solution, and the capacity to deploy this solution into real-life systems. So now here is a short pictures of the BB4 platforms involved in Pilot 3. So we have the platform from Huawei, the Atlas 500 Pro, that's enable fast vision processing. We are at the middle of the Soki platforms, which is a TSN switch based on FPGA. And us, Unimore, we bring the two platforms, so modern edge platform that you can see on the left, and platforms where we simulate sensors and camera. And in the following slide, I will mostly focus on this platform. But first, before presenting these platforms and the technology inside, I will present some keywords and points that are important to understand the followings. So first one is the time-sensitive networking, TSN. So it comes due to the fact that standard Ethernet communication are not predictable. So the I3E TSN protocols helps to determine communication, scalability. It supports flexible configuration. It also enables bandwidth reservation and also helps to interoperability with legacy network. The other point that I will present, it's the hypervisor Jailhouse. It's the hypervisor we use in our solution. It's developed and maintained by TMNs. It's a type 1 hypervisor. So it is open source. It has a minimal runtime code and does not perform emulation or scheduling. It has a static partitioning, so it means that one VM, when a resource is assigned to one VM, it cannot be assigned to another one. So we have CPU isolation. So it means that on the platform, the maximum number of VM available, it's the numbers of core available on the platform. Also, Jailhouse brings communication mechanism between the VM. It's called the IV shared memory mechanism, and so it's not really, it allows sharing of memory between VM. Also, Jailhouse simplifies the certification process, and it also requires Linux to boot up and use the root cell, so the Linux, to control other virtual machines. On the right, I present in 2 steps the booting of a system with Jailhouse. So first, you will have standard Linux system that will boot, so Linux boot, and after that, Jailhouse will be enabled by a kernel module of Linux, and he will insert himself between Linux and the hardware. In the second step, he will use the Linux as the root cell, and will remove some of the resources assigned to the root cell to create inmate cell, which is the partition where the inmates, so the name of the virtual machine under Jailhouse, so to create this partition. And after that, inside this cell, it will start the different virtual machine. And this virtual machine can be bare metal application, RTOS, or Linux operating system. Now, I will present the virtual time-sensitive networks. It's a technology that Unimore developed. It's based on the fact that hypervisor with non-pure visualization cannot share specific resources, like Jailhouse, for example. And on some platforms, you will have, for example, multiple VM, which want to have an Ethernet connection, a TSN connection. But on these platforms, there is less Ethernet ports than the number of VM we want. And so normally it's not feasible to do that. So here is the solution of Unimore, so VTSN. This solution is based on an Ethernet port, so we need an Ethernet port to reserve for that technology, and also a virtual machine dedicated to simulate a TSN switch, and the IVM shared memory mechanism, so the mechanism I told you before, and of course the TSN protocols and Jailhouse. So on the right, you can see the layout of this solution. So you will have all the virtual machines which shared memory on the systems, and also the virtual machine that act as the TSN switch, which has access to the Ethernet ports. And with the shared memory mechanism, it will simulate an Ethernet port, TSN port, for all the VM on the platform. So now talk about the pilot 3 of Emoco. So our goal was to simulate the camera and the sensors from the blade inside the pilot 3. To do that, we choose to do it on a ZCU102 from Xilinx UltraScale Zinc Plus. No, Zinc UltraScale Plus, sorry. So we decide to use a virtualization-based solution to have 2 virtual machines, one for the camera, another one from the sensor, and allow for them TSN features to discuss with the TSN switch from Soki. And why we choose a virtualization-based solution is because a virtualization-based solution brings isolation, resource optimization, predictability, and also flexibility. For example, if you want to modify one application, you can change the ecosystem in a VM without modifying the behavior of the other VM. And also bring TSN access to enforce timing guarantees and manage mixed critical traffics, and also improve network stability. However, we have an issues for that. It's that the ZCU102 has only one Ethernet port. So it's the advantage of a virtual TSN. It's that it allows us to use the ZCU with the 2 VM and allow the 2 VM to use TSN connection. So we add to this system another VM, which is the VTSN switch. And with this help, we also modified the VM of the camera and the VM of the sensors to use this TSN connection, like I present with the TSN slide. And also, because there is 4 core on this platform, we add the possibility to use this last core to create another VM, which will act as the actuators of the machine. So this technology, so the VTSN solution, can bring some advantages for the packaging machine sectors, because it allows software-defined central control units. So it means that a new software component can be deployed as VMs, and so no need for additional hardware or links between platforms. And also it is the migration from a proprietary feed bus to TSN. So TSN infrastructure can virtually grow independently from the physical networks. It also optimizes cost and hardware usage in constrained environment, which TSN connection can be consolidated. And also bring a predictable inter-VM communication. Each VTSN port is independently configurable, and the virtual Ethernet interfaces act as a TSN native virtual links, as I told you. So the features of this developed technology is to port to real-time core, for example, the Cortex-A5, and also support different platforms like AMX8 or NVIDIA platforms like the Jetson, for example. It can be used also, it can be, these 2 points are important because on NVIDIA platforms, so the Jetson, for example, there is a Cortex-A5, and this Cortex can be used to simulate let's say, to embed the virtual TSN switch, and the other ARM kernel core, for example, can be used by Jailhouse to create the other virtual machine. Also, we will implement additional TSN protocols and DDS layers. And an open question for us is how to combine the quality of service of DDS layers with TSN. So it's all from my side, and now I will let Daniel continue the presentation.
Okay, so thank you, Ricardo, and thank you everyone for attending this webinar. My name is Daniel Uribe. I'm from the company SOC-E, and I'm going to be talking about the TSN platform based on FPGA that we have developed for this project. Okay, so for the scope of the project, we have designed and developed a high-end processing and communication hardware platform based on a system on programmable chip, which will allow to fulfill requirements with a compute-intensive workload and communications with real-time and advanced requirements. Okay, so the SOPC selected for the platform is one of the Xilinx AMD Sync UltraScale MPSoC. And with this, we will be able to support implementations of TSN IP cores with a high number of communication ports. And by the usage of this technology, we will be able to combine critical and best effort traffic in a unique, deterministic, and interoperable Ethernet network. This is very important. This is very important because with this feature that I just mentioned, we can offer significant cost reductions in terms of equipment investment, maintenance, seamless integration, and single vendor dependence reduction. Okay, if we focus on the hardware platform, as I said, it is based on an SOPC from Xilinx AMD. Therefore, we have a reprogrammable chip, which is very useful for this kind of TSN implementation because we will be able to implement different designs with high number of communication ports and with different kind of functionalities required by any of the use cases. Okay. And when we talk specifically about the hardware, there are different features that we have taken into account for the development of the platform. Being those, for example, the support of copper and fiber optic physical communication interfaces, support for up to 10 gigabit per second line rates, also, the implementation of an SOPC, which has a programmable logic along with a processing system on the same chip, will facilitate the implementation of software and hardware computing units for the execution of AI algorithms. Additionally, the platform have been developed with a conduction heat dissipation to avoid the usage of fans and ensure the operation over a wide temperature range. Okay, if we keep talking about the technology that we have implemented inside the SOC or the SOPC, we have a TSN layer 2 switch. Okay, TSN, time-sensitive networking, is a technology that has been developed by the IEEE as a set of standards, okay? And the purpose of these standards is to enhance the traditional Ethernet communication bus to provide capabilities of real-time and high availability. It is really a great technology because the main purpose of this technology is to allow to merge different kind of networks into the same one, which will allow us to merge the OT and IT without any problem and keeping the deterministic and real-time capabilities for the specific traffic types. Additionally, as this is a technology that is developed using open standards, this will also help the reduction of cost and will also help to avoid the proprietary solutions, which usually involves an increased cost. Okay. As I mentioned before, this TSN technology is not just one standard; it's a set of standards, and basically what we are looking in the screen now is some of them, and those are the ones supported by our TSN solution. Okay, For example, there are mechanisms for time synchronizations, such as 802.1 AES, or mechanisms for traffic shapers, such as 802.1 QAB or 802.1 QBB, or mechanisms for redundancy, security, and high availability, such as 802.1 CB or 802.1 QCI. There are more and more standards, some of them related to configuration, such as QCC and some others, okay? Okay, and in the scope of this project, in the context of the Pilot 3, this platform is going to be used as a central processing and bridging unit into the Pilot 3. The platform is going to bridge the preprocessed data as an edge element to the fog for an ulterior processing based on a Kafka system. Additionally, as we have implemented the TSN layer 2 switch, the platform is going also serve as communication interface between all the rest of the components of the Pilot 3. Okay, and additionally, this platform is going to provide some quality of service to the network using some of the TSN mechanisms that I have presented previously. Okay, when we talk about how we can leverage this technology into the packaging machine sector, we have already identified some of the challenges that can be solved by the usage of our technology. Those challenges are, for example, the increasing demand for high availability protocols with real-time capacity in the packaging machine sector, or, for example, the merging of OT and IT, which will come along with an increasing bandwidth needs in this kind of networks. There is also some needs for equipment with medium-high degree of robustness and the operating capacity in an extended temperature range demands. Well, the first two challenges, as I mentioned before, can be easily solved with the TSN technology implemented in our IP cores, because with this technology, it is possible to merge different kinds of networks into the same one by maintaining the criticality levels of some of the traffic flows. Okay, this is very helpful because as I mentioned, this is covering the first two challenges. Additionally, for the other two challenges, our platform has been designed with robustness in mind and with the heat dissipation in mind as well. So this is also why we can offer a robust and fanless hardware platform. And when we look at the future, we have also identified different improvements that can be achieved with this technology. And well, if we focus on TSN, let's say that this technology has still a lot of ongoing projects with many standards still to be finalized, and that's why we will also need to be there to implement all the required mechanisms. This is a technology that I would say it's already in a very finalized state, but as the technology is becoming more popular and a lot of sectors are implementing this technology, new needs for different use cases are still being required, and that is why the new ongoing projects are still there. And that's what I mean with this. We also, as technology providers, we want to stay on the last of the developments. Additionally, as TSN is in the focus point of different sectors, such as industrial automation, the automotive sector, or the aerospace sector, which also have their specific requirements due to their specific or particular use cases, we will also need to cover all these kind of requirements specific for each industry and be able to provide a solution for all of them. And one final improvement that we have identified for this technology is the development of an end equipment with a full metal enclosure that will be able to be implemented in any location with a wide range of temperatures and environmental conditions. And that's all from my side. Ricardo, I give you again the
Thank you very
presentation.
much, Daniel. And it's now the turn of Lorenzo from Evidence Huawei that will present the other hardware component of the real-time smart control platform, that is the Huawei Atlas 500 Pro. Lorenzo, the stage is yours.
Okay. I'm Lorenzo Diana from Evidence, a company located in Pisa, Italy. And now I will introduce you what we are doing inside the IMOCO 43 European project and inside the Pilot 3 led by CRIT. So the Huawei Atlas is a series of products aiming to cover different scenarios from edge to server solution. It consists of different devices such as PCI Express cards, edge device, server devices. And the goal is to provide all scenario artificial intelligence infrastructure from edge to cloud for both training and inference of deep learning artificial intelligence model. In Pilot 3, we choose to use the Atlas 500 Pro to provide low inference artificial intelligence task. In particular, the Atlas 500 Pro can be deployed at the edge to meet application requirements in complex scenarios such as transportation, campus, shopping malls, and supermarket, thanks to his computing performance and environmental adaptability. This device is also easy to maintain and provide edge and cloud collaboration. Its computing capabilities consist of a CPU, Kunpeng 920, with 64 core based on ARM architecture. And for artificial intelligence inference, this device can feature up to 4 Atlas 300i PCI card, according to the requirement of the scenario addressed. Its power consumption is quite efficient thanks to both the ARM-based CPU and the Ashen chip we can find inside the Atlas 300i inference card. To be able to run a neural network on this kind of device on the Atlas platform, we have two main options. The first one is to develop the neural network using the Mindspore framework. That is a deep learning framework provided, an open source deep learning framework provided by Huawei that allows easy development and efficient execution for many different scenarios of artificial intelligence tasks. This framework supports all the devices provided by Huawei, so all the Atlas devices. And there is also a models repository that provide different state-of-the-art neural network model that are already trained and ready to be deployed. Is to develop and train the neural network using third-party frameworks such as TensorFlow or PyTorch, and then import the neural network using some dedicated tools able to apply conversion and tuning to the neural network in order to make it suitable to run on the Atlas devices. Moreover, third-party framework adaptation layers are provided for both TensorFlow and PyTorch. In particular, inside the MOCO project, the goal of Evidence is to develop a multi-operating system solution based on this device, the Atlas 500 Pro. This device has many core CPU, as I already said. So the goal is to dedicate some CPU to the guest operating system, that is a Linux operating system, and the host operating system. And as a guest, we want to use FreeRTOS virtualized via KVM in order to provide a real-time capability. Moreover, this device can provide hardware acceleration for neural network using the Ashen chips, and also low latency communication using time-sensitive networking. Moreover, general purpose capability are provided by the standard Linux environment. We are developing this solution, and the result of this development is that the proposed solution can run neural network inference on the Linux operating system using the Huawei Ocean chips, and neural network using third-party framework can be easily converted into a format suitable to run on this device. And thanks to the standard Linux environment, it is possible to integrate this device inside the scenarios required by different pilots, for example. Then FreeRTOS run on the proposed device, and we provide a shared memory mechanism to allow data exchange between Linux and FreeRTOS, and also event-based communication to trigger behavior or other things like that. Inside the pilot thread, Heavy used this solution to provide hardware acceleration for neural network and Ethernet-based low-latency communication. Concerning the artificial intelligence task, Digital Twin Technology, a partner of the MOCO project, has developed and trained a neural network to perform anomaly detection for the Pilot 3 scenario. And Evidence uses the Huawei tool to import and tune this neural network and to run it on the Atlas 500 Pro. During the integration test of the Pilot 3, the Atlas was used to perform low latency inference and using the neural network provided by Digital Twin Technology. In particular, on board the Atlas device, we can collect input images from a virtual camera connected via Ethernet, and images are collected using the GStreamer tool. Then we can apply pre-processing on the images, such as resize, rescaling, or channel adjustment as needed. And then we can feed the neural network with the pre-processed images and collect the output, packet the output in a Kafka message, and send this message to a Fog server where other algorithm can be used or data can be stored for future needs. Concerning the Ethernet-based communication, the Atlas 500 Pro can be configured to use time-sensitive networking by its own, thanks to the Linux OS and the network interface controller that can be configured to this purpose. So in order to provide different bandwidth for different stream of data. In particular, inside the pilot thread, there is the need to enforce TSN communication among all the connected devices. So as we just saw, the partner SOC provided a router able to enforce TSN communication for all devices on the local network. Here we can see a high-level view of the logical architecture of the Pilot 3 concerning the Atlas 500 Pro. The SOC router handled the Ethernet connection between all the devices, and in particular, the Atlas 500 Pro received the images from a virtual camera provided by Unimore. In particular, industrial machines such as packaging machine can employ artificial intelligence application to improve the production process. For example, they can use predictive maintenance to reduce the downtime of machine or by identifying the end of life of hardware components. They can use anomaly detection to improve the quality check of the product at different stages and enable early detection of malfunctions. Or they can use object detection to improve the traceability of the product inside the machine, and etc. etc. There are a lot of applications that can be enabled by artificial intelligence. In low latency Ethernet-based communication can be used to send punctual updates of the machine status to a decentralized system where high-level policies can be applied. For example, policies taking into consideration the current status of many machine, or to fed a digital twin model of the machine or the entire facility. And to this aim, low latency communication are crucial to have good results. Moreover, the proposed platform can be adapted to different use cases concerning packaged machine and other industrial machines. The solution represents an all-in-one solution to increase edge computation capabilities by providing high efficiency thanks to the ARM-based CPU and the Huawei Ashen chip, and flexibility thanks to the Linux operating system and the variable number of Ashen chips that can be installed. As a future for this technology, well, we see that the proposed solution can be employed in any scenario requiring artificial intelligence acceleration, low latency Ethernet-based communication, real-time capability, and general purpose capability. And the flexibility of the proposed solution make it beneficial for many industrial scenarios requiring the above-mentioned features. And as a future step, we can include, for example, improve the performance of the virtualized operating system, for example, the communication capability between the guest and host operating system or with the outside system. And that's all from my side.
Thank you very much, Lorenzo. Now we can move from the more physical layer, physical control layer, let's say, as we indicated in Imoco, to the network layer with Tassos of GNT.
Okay, hello, my name is Tassos Kanellos. I represent GNT, which is a partner in the Imoco 4E project. And in this session, I will be talking about two components that we are contributing to Pilot 3, which are the distributed messaging system and the big data repository. So both of these components, they are actually part of one of the 10 building blocks that make up the entire Imoco framework. Specifically, they are part of building block 9 that has a rather central position in the overall Imoco framework, and its main purpose is to serve data communication and management needs in the upper layers of the Imoco 4E framework. So in terms of positioning of these components in the architecture of Pilot 3, this is where we are. This is the upper layer that represents the fog server that has been employed in the infrastructure of Pilot 3. So the lower layers, they refer to the edge environment and edge devices. Our distributed messaging system and big data repository is on the fog server. So these are actually the two components I will be speaking about, the DMS, the distributed messaging system, and the big data repository, but they are also complemented by another couple of components that I will also refer to. But I will start with a distributed messaging system, or DMS, which we consider to be the backbone of the entire building block 9. So just to put things in a little bit context and explain why this technology is useful, in an IoT environment, it is very common to have components that need to exchange data over the network, and we can refer to these the components that provide the data as data producers and the ones that receive it as data consumers. So such examples in an industrial IoT context could be we can have data producers being sensors, and then the data would be consumed by, for example, AI components. Or in another case, we can assume that we have data producers that are AI components, which produce inference results that in turn need to be consumed by some other software or hardware that controls some device, like an industrial control mechanism at the edge. So if we were to try to establish direct communications, one-to-one communications between multiple producers and consumers, this would quickly lead to a big mess if we were trying to scale up and if we had multiple such components. For example, one first difficulty we would have was just to keep track of the different IP and ports of the different services and components for managing all this communication. So this approach is not really suitable in an IoT context, direct network communications. And this is why with this technology, we want to introduce a PubSub messaging system. And in fact, the DMS, it manages all this communication complexity between multiple endpoints by introducing the publication subscription messaging system. The most important advantage that this technology brings is that it provides a loose coupling between communicating entities. This is really important in complex configurations and complex systems. And in this case, we introduce a message broker that acts as a mediator in the communication between producers and consumers. And this pattern is highly scalable. All producers and consumers of data, they only need to connect to the message broker, which makes it, for example, very easy to add more instances of the same services or new services. Now, in order to drive this message broker, we use Apache Kafka technology as the underlying technology. Apache Kafka is an open source distributed event streaming platform. And the way it works is that it basically handles text-based messages. Information is organized into topics, and any producer can publish any information that it wants to a specific topic on the Kafka broker, and then any consumer can subscribe to that topic or any other topic and receive the information that is published on that topic. So this is the very general way that it works, and it has some very significant advantages, including the possibility to have a very high throughput, which of course also depends on the underlying infrastructure that hosts the Apache Kafka cluster. It is also highly scalable, and we can have production clusters that involve thousands of brokers, trillions of messages per day, petabytes of data, and so on. It is also an open source technology, and it allows self-managed and on-site deployment, which is of particular interest, for example, in Pilot 3, where we want the entire deployment of the system to be on-site. It is highly customizable. It is very interoperable and easy to adopt. And there are already many integrations of Apache Kafka with other third-party systems and programming language, for example. It is also highly reliable and fault tolerant. It has many mechanisms to provide this, and it is also battle proven in the sense that it is very widely adopted in large-scale production environments for many years now. So this is what things start to look like when we have many producers and consumers connect to a Kafka broker. In fact, we can have components that act as both consumers and producers. And putting things in a little bit more context of Pilot 3, where we have an edge layer, which is rendered here at the left, and a fog layer here at the right. So this big rectangle here that represents a fog server, which hosts the Kafka broker, which can communicate with components that are on the same server or on other devices. And here, for example, in Pilot 3, we have some anomaly detection component at the edge, another AI components at the fog that exchange information with the Kafka broker. Then I would also like to refer to this component here, which is the distributed messaging system field gateway proxy. Now, this is developed by Unimore, represented by Fabian, who spoke earlier. And this, in a sense, complements the DMS because it acts as a proxy of the DMS at the edge. And it serves as a middleware abstraction layer, allowing components from edge platforms to communicate with a distributed messaging system that resides at a higher infrastructure layer, the fog or cloud. And it also can be used as an adapter for legacy devices and software in brownfield architectures where communication protocols cannot be changed to directly adopt the Kafka PubSub system. And another functionality that it can provide is that it can do data consolidation, data filtering, and data transformation operations in the data it handles upon demand. Then I will move on to the other basic technology that we are contributing, which is the big data repository. Here, all information that is exchanged on the Kafka message broker can potentially be intercepted and ingested and permanently stored in an Elasticsearch repository. So then the data that is stored here can be accessed by all components that need to consume it asynchronously. For example, we can store the sensor data that can then be accessed by AI components in a training mode, for example, or to perform some long-term data analytics. Then we can also introduce pre-processing operations in this ingestion pipeline to be performed on data before it is permanently stored. And the technology we use, the underlying technology for driving the big data repository is Elasticsearch, and some of its advantages include high scalability and interoperability. It has a distributed fast performance. It includes a versatile and very powerful search engine, and it's RESTful and schema-free design, and it is open source. Then finally, another component that complements these two is the data visualization toolkit, which is developed by ITML and integrated by GNT. It complements both the DMS and the BDR in the sense that it provides some visualization tools for these specifically. So we use the Grafana tool for visualizing real-time data that is handled by the distributed messaging system. And we can also use Grafana for generating alerts and notifications either by email or by integrating them with the instant messaging platforms. And on the other hand, we can provide the Kibana tool, which can be used for visualizing historical data that is stored at the big data repository. And we have, in fact, used both of them to create visualizations and dashboards for the needs of Pilot 3, which we can have a look at here. So, for example, this is a dashboard that made in Grafana that is used for visualizing some key health and performance metrics of the deployment of the distributed messaging system, so of the Apache Kafka cluster. This dashboard is specifically built for visualizing the data from the sensors in the upper part here, and then some inference results by one of the AI components employed for Pilot 3. And here at the bottom, we can actually see this one of these inference results in more detail. This is the reconstruction error for the anomaly detection provided by one of the AI components for predictive maintenance. And at the lower left here is the inference calculation time by the same components, or the latency of that component. And at the top here, we can see one of the possible integrations we can have for alerts. So we can configure alert policies and integrate with instant messaging services such as Telegram in this case for delivering notifications to the user. And then finally, this is the Kibana tool. Here we have a dashboard for visualizing some historical data that have been stored. In this case, these are, again, related to an AI component. And another view that we can set up in Kibana is this kind of tabular view, which can be used for inspecting individual entries, in this case, some data points from the sensors. And this is it, basically, regarding the implementation of building block 9 components in Pilot 3. I think this covers it. And I think I can jump directly to the next session, if you agree, Ricardo.
Yes, of course. Of course, Tassos, thank you.
Which is about anomaly detection for predictive maintenance. So by this, by predictive maintenance based on anomaly detection, basically we refer to an analysis of sensor data using artificial intelligence techniques to detect specific patterns and early warning signs in order to predict problems before they occur in the industrial equipment. So from our side, from the side of GNT, and in fact in collaboration with another partner, ITML, we have implemented two approaches for anomaly detection in predictive maintenance. On one hand, we have a component that is intended to be deployed in a fog or cloud environment, and that is a long short-term memory auto-encoded deep learning model. And the second approach we have taken is more oriented towards edge environments, and this one is based on a clustering and classification approach. Now, for both these approaches, both resulting components have been based on the same data sets. which refer to sensor data from a Vega shrink wrapper machine by Ocme. These datasets are available from Kaggle. And there are, in fact, two datasets from this device that we have considered, which I will now refer to in a little bit more detail. The first dataset is a labeled dataset that has specific snippets from such a device that has a new blade installed, and there are some other datasets, some other snippets from a machine that has a worn, a rather used blade installed. So these are very clearly labeled, although they are limited in size. We only have 3 snippets from a healthy blade and 3 from a worn one. Now, the other data set that we considered was more longitudinal in a sense. It is from an entire 1-year operation of a machine. And this one includes 518 such snippets. And in both cases, there are 7 features in each sample, in each data point. This one actually has an 8th one more. So I will now talk about the first approach we have taken, which is oriented for deployment in a cloud or fog environment, which is to say an environment where we are less constrained in terms of computational resources. And for such cases, we have proposed a deep learning approach that combines an autoencoder model with a sequential network, and specifically a long short-term memory network. Now, so more details about the autoencoder model in general. One of its advantages is that it provides a single model that can learn at the same time both features and representation of normality, which means that it can learn feature representations of normality. And this is not possible, for example, in other deep learning approaches for anomaly detection. It can also learn low-dimensional representation of features. It uses data reconstruction errors to define anomaly scoring functions. It presupposes that normal instances are more accurate than anomalies. And it also allows the integration of deep learning networks of all types, including convolutional neural networks and recurrent neural networks. And a few more details about the long short-term memory networks. So being a sequential model, an LSTM network is able to capture temporal dependencies in time series data. This is particularly important and of significance in the context of Pilot 3, where we are meant to analyze time series data from sensors. It also allows information persistence that is valuable for capturing temporal dependencies, again, important for the same reason. And it is quite similar to recurrent neural networks, but it is considered to perform better in tracking long-term dependencies in the data. So it addresses the vanishing gradient problem. Then another feature is that it can maintain data in memory for long periods and makes them this makes LSTM networks highly applicable for sequential data processing, such as sensor data stream analysis. Now, this model, we have used it, we have implemented an anomaly detection mechanism for this model that uses anomaly scores, as opposed to just a binary label that is less informative. So that would be just classifying something as being an anomaly or not. So an anomaly scores has a more granular, a more gradient information hidden behind it. And the anomaly scoring is calibrated using the reconstruction error for the normal representation, and values that exceed a threshold are marked as anomalies. Reconstruction errors of the normal data are modeled as a Gaussian multivariate distribution, and the anomaly score for new data points are calculated using the Mahalanobis distance, which is essentially a distance between a point and a distribution. And at the right here, you can see the application of this mechanism in the data set. And here you can see that the threshold that has been calculated is represented here with this horizontal line, and the data points above this are classified as anomalies. Now, we have also introduced some specific optimizations and customizations to the, let's say, more generic version of the LSTM autoencoder model. The first one is that we have introduced an adaptive anomaly scoring thresholding function. So in this case, we do not have a static threshold, but it is rather determined through the maximization of the weighted average of precision and recall, which is basically the F beta score. We have also performed some considerable hyperparameter tuning. We have specifically used Bayesian optimization to select values for multiple parameters of the LSTM autoencoder model to maximize its performance. Thirdly, we have also done some work in determining an optimal sequence length. So in the sense of the number of time steps that the LSTM network will consider at any given time during training or inference. And here we have tried to find a balance between computational efficiency and model performance. And finally, we have done some work with a calculation of the F beta score that I mentioned previously. And this basically determines the balance between precision and recall in an anomaly detection model. And as I said, it also indirectly influences the thresholding calculation. So with all this, we have tested the model we developed in the first data set, the new WARN data set. This has been employed for supervised or semi-supervised training and evaluation. And in order to proceed, we established a model training and evaluation strategy that was based on a reorganization or splitting of the data that was available into 7 different groups with different purposes, in its case, for training, validation, evaluation, and either being a normal or anomalous data or a mixed data inside. This table here in the middle shows the hyperparameter values that we arrived at after running this optimization procedures. And at the right here, we can see some final evaluation results of the model in some of the cases. So at the top is the when we tested it against the anomalous dataset that we have reserved for validation. Here is the results for validation reserved for the dataset reserved for validation on the mixed use case. And as you can see, the results are quite excellent. We managed to achieve a 100% score in accuracy, precision, F1, and recall, which is, of course, very good. But on the other hand, we also need to consider that the dataset was quite limited. And as we discovered, the labeled dataset, the new and the WARN variants, they had some features that were very clearly distinguishable from each other. So we managed to achieve such high scores. But of course, we need to be cautious about whether this can be generalized easily in some other data set. Now, we also tried to make some experiments using the 1-year data set. However, here we were even more limited because we could only use this for more informal verification purposes due to the labeling ambiguity present in this data. So we also had to make some hypotheses for the training of the model. So we assumed that the first month of the data referred to a healthy blade, and the last month, month 12, refers to a worn blade. So that we would have anomalous data. And training the model based on this hypothesis, this is what we managed to get over the period of 12 months. This is a plot of the anomaly scores that we got for the entire 12-month period. And we also tried to fit a line using regression over these data. And we can notice here that there seems to be an increasing trend of anomaly score over the 12-month period. And also we can see that there is some kind of extreme peak here in month 4, but this, in our opinion, agrees with the some outliers that were detected in one of the specific features in the data set. And then finally, we also implemented a logistic function for calculating a system health, which ranges from a 0 to 100 scale. And this is to have something more intuitive, more human readable. That makes some sense. And this is the result has been plotted here with a red line. So this is the system health ranging from 100 to 0. And we can also observe here that the health seems to somehow degrade over time during the 12 months. And we can also notice that there are increasingly frequent and severe declines over time. So these negative spikes here, you can see they become more frequent and more and go lower. That's it basically for the first component for the LSTM autoencoder. And now I will jump to the second one, which is oriented towards edge environments. So in this case, we are using clustering analysis on unlabeled data sets to determine classification categories. In our case, we are interested in normal and anomalous data. And based on the clusters we can identify, we can train a classifier machine learning model, which can then be deployed at the edge so that it can predict the category of new incoming data points in real time. So here also you can see this kind of internal software engineering viewpoint, or the architecture of this component and how it is integrated. I have not referred to the equivalent diagram in the previous component, because at the end there is a common diagram for both components. And I will discuss this in more detail. Now, the motivation behind this approach, this AI component, is that we wanted to try to use clustering to determine normal and anomalous data in labeled data sets. So in a sense, employ unsupervised learning. And also, we thought to use this approach because it would lead to a lightweight classification model that can run on edge devices which have constrained resources. However, there was at the same time a challenge associated with this approach, because clustering typically is not really suitable for analyzing time series data. So the way we thought to work around this problem was to use time window processing so that we can try to capture temporal dependencies and patterns within the time series data. So this is the approach we took. In fact, for the clustering part, we tried 3 different algorithms: k-means, affinity propagation, and min shift. And we also tried 3 different sizes of the time window for the time window processing. So we tried 50, 250, and 500 samples in the time window in each case. And in this table at the lower left here, we try to evaluate the clustering performance of these different combinations. So for the different sizes of the time window and the different clustering algorithms, we evaluated the clustering performance using the silhouette value, Kalinsky-Harabaz index, and Davis-Baldwin index. And we concluded that the k-means algorithm seems to be working, seems to have the best performance. Then we also tested the classification performance of the resulting classifier based on the k-means clustering algorithm. And here we noticed that when using a time window size of 500 samples, it seems that it actually decreases performance. Whereas when comparing the size of 50 to 250 samples, the difference is almost negligible. It is only very marginal. So, and in the end, with the combination we selected was the k-means clustering algorithm along with a size of 50 samples. And here we have some efficiency metrics for this combination when running the classifier on the Jetson or in Nano. So the time it takes to process a single data point, but we need to be aware that the single data points means 50 samples. So pre-processing 50 samples and performing the inference, that takes 55 milliseconds. So we can have a throughput of 18 data points per second with a load on the CPU of the Jetson at 17% and a RAM consumption of 192 megabytes. Finally, won't take very long. This is the last slide. This is the diagram I was referring to. This is how things fit together from an integration point of view or a systems engineering point of view. At the lower right here, you can see the clustering and classification component, which is deployed at the edge. So underneath this dashed line is the edge environment, above is the fog environment. So this is the clustering and classification. And this gray box here is the long short-term memory autoencoder component. And you can see here that in the first case, we have feeding sensor data directly to the component. In the other case, the central simulation we are using, it sends the data to the field gateway proxy, which also resides at the edge, which in turn propagates this data to the distributed messaging system at the fog server. And then the LSTM autoencoder component consumes this data from the Kafka cluster here. And then both these AI components, both the clustering and classification and the LSTM AE component, they provide their inference results as Kafka messages to this Kafka cluster here. And in turn, these are ingested to the big data repository for persistent storage in Elasticsearch. And then we can also have these Grafana and Kibana visualizations that we talked about previously. And that's it from my side. Thank you for your time.
So I will leave the floor to Dario now from University of Sassari.
Good morning, everyone. I am Dario Guidotti from University of Sassari, and I will briefly present the algorithm we developed for anomaly detection. Well, I will not be too long on autoencoders because Tassos already presented how the model works. So you have a classical fully connected neural networks in this example, which encodes the characteristic of the input space defined by the input dataset in a smaller latent space, and then decodes this latent space to the output. If the input and the output are the same, what happens? Happens that when the input data are anomalous, the predicted output is basically more distant from the input we would like to predict. Therefore, if you compute the vector reconstruction error, so some kind of difference between the output predicted by the network and the input provided to the network, you can have a measure of how anomalous are the data you are considering. The use case is the same as the one presented by Tassos, and in particular, we worked only on the unlabeled dataset. Our hypothesis on this, using a bit of data analysis, was just to take the data related to the first month provided in the dataset to train our autoencoders, because as you can imagine, we don't need to know which particular data are anomalous, but we need to know that the data we are using to train our autoencoder are not anomalous. And so the first month was a kind of, let's say, reasonable hypothesis. Well, then we trained our network and we first considered, let's say, the mean square error, so a standard measure of how good the network is with respect to the data using during training for 4 different small network architecture with an increasing number of neurons in its 3 hidden layers and with the standard ReLU activation functions. We tried to keep the network, as you can see, very, let's say, simple, not complex network architecture, because our aim was, after training, to formally verify the network developed in order to be able to give some kind of formal guarantee on the behavior of these networks. Well, as you can see, Curious thing, given the trend of current, let's say, neural network, the smaller model were able to reach a better mean square error than the bigger models. Okay, obviously, this kind of results is good to have an idea if our autoencoder is able to correctly predict, let's say, the data from the normal functioning of the machine. But it doesn't say anything about if our autoencoder is able to detect the anomalous data. To be able to, let's say something about this last behavior of the autoencoders, we computed the vector reconstruction error on the whole data set of interest, and we plotted it. And from our plots, it appears clear that the major anomaly present in the working in the data set is during month 4, okay, and it is clearly, let's say, detected by all the autoencoder considered. And after, let's say, some research on other people which used the data set, which, as you heard, is a public data set on Kaggle, we deduced that at month 4, the blade was changed. And therefore, you have this kind of big anomaly, because basically during month 4, the blade failed and was changed, and then it worked again correctly. These minor anomalies you see during the following months should be based on the change of mode of the machine from our, let's say, experiment. If you, let's say, color the plot with a different color for each mode of the machine, of the packaging machine, you see that this small, let's say, peak in the vector reconstruction error correspond to changing the mode of the machine. Okay, so clearly in, let's say, our inference software, when the prediction of our autoencoder surpasses a certain reconstruction error, then we can identify that data point as an anomaly. Our algorithm basically communicate with the distributed messaging system by GMT, which forward us the sensor data of the machine, and then we respond with some information regarding the anomaly, in particular the vector reconstruction error and the flag which indicates if the particular data point is to be considered anomalous or not. And then the information is propagated to the rest of the IMOCO framework. The benefit of this kind of algorithm, well, were already said by Riccardo at the beginning of the presentation, but in general, why we want to detect earlier eventual anomaly in the machine? Well, it's because it ensures that the product is consistent, the product quality is consistent. We can minimize the downtimes and maximize the operational efficiency, and we can maintain the machinery in a proactive way instead of a reactive way. Again, this kind of technology, given that they are a very small, very simple neural network, can basically applied to more or less any kind of platform, and therefore it has a quite a lot of potential application. And obviously, the anomaly information can be used in some kind also of monitoring dashboard for human users. And that's it. Basically, for the future, some kind of things that can be done to, let's say, enhance this kind of techniques is clearly some kind of predictive analytics to forecast the machinery failures because they occur. For this, you need some kind of let's say, model which can predict the values of the sensor data in the future, given the past sensor data. And then we can also think about optimizing the maintenance schedule based on the results of this kind of algorithm. And finally, right now, this algorithm must be trained for a particular system. And if the system is subject to some kind of change, there is the not trivial risk that the algorithm do not work so well anymore. So some kind of reinforcement learning techniques, or in general, online learning. So some kind of algorithm which keeps learning during its functioning, let's say, could be useful for adaptive and autonomous system optimization. And that's it. If you have any question or...
Thank you very much, Dario. And now I will move to the last presentation that will be done by Tariq from Digital Twin Technology. And these are about the AI algorithm developed for image anomaly detection, the other kind of data stream that we have in Pilot 3. Tariq, the stage is yours.
Good morning, everyone. So my name is Tariq Islam. I'm an R&D project manager at the Digital Twin Technology in Germany. So I will talk on the topic enhancing product quality control process using image anomaly detection ML model. So at first, a brief introduction of our company. So DTT is an SME located in Cologne, Germany, and it was founded about 6 years ago. Our vision is to develop advanced open source digital twins for smart city industry image anomaly detection ML model in the context of Pilot 3. And after that, I will briefly present our technology for the packaging sectors. And finally, I will talk about the future of our technology in this industry. So let's start. After all these presentations, we now know that the predictive maintenance is very important in all the manufacturing processes. It actually helps to optimize the resources and the time in several of the manufacturing steps or the processes. To address this, we have developed an image anomaly detection ML model using autoencoder on the vision data. It helps like to detect the faults in an early stage, and it is actually tailored for the bottle packaging industry. And this model is developed using the frameworks like TensorFlow and Keras. and we have integrated this model into a digital twin for achieving optimal reliability. And apart from this, we have actually deployed this model on Edge and also on a fog platform with the help from Unimore. And we have also created or developed an user interface for the visualization of the prediction output. So here I actually present the steps of building the autoencoder ML model. We developed again this model using the TensorFlow and the Keras, and then trained the model on the bottle dataset. So in this figure, so you can actually see a glimpse of the dataset, and it contains images with and without the contaminations like broken rims or decolorifications or the residues which can be seen on the last row of this image. So my previous speakers have already explained the details of the autoencoder models. Yeah, I don't want to actually now go through the details of the structure or the architecture of the model. So it basically contains two main modules, an encoder and a decoder, and finally reconstruction error is actually calculated, and if this error is above a certain threshold, it then actually reports that okay, this image contains anomaly. If not, then it is not an anomaly. So this is like the basic idea of the architecture of the autoencoder ML model. So with implementing this model on this bottle dataset, we initially obtained a prediction accuracy of about 70%. Then we actually applied some optimization processes such as augmentation. It includes scaling, rotation, and using different light modes, etc., to actually augment the data sets. And then we also actually applied some different batch size, and then we also tuned the hyperparameters, such as we tried out the learning rates, the different learning rates, and we tried with the different number of dropout scores and such approaches. And finally, we achieved prediction accuracy of 88% with a precision and a recall value of 75% and 85% respectively. Here I will show you a small clip showing the initial demo of our algorithms performance on a standalone machine. I hope that you are able to see the clip clearly. So on this image, so it doesn't actually contain any anomalies. So the prediction was that no, it doesn't contain any anomalies. And in the next image, so we'll actually see that it has some anomaly, and the model is correctly predicting that okay, this model has image has anomaly in it. Okay, now here, okay, so it's still playing. Let's stop it. Okay, okay, let's now talk about the development of our model in the context of pilot 3. So this model detection is actually a part of pilot 3 and also a part of digital twin for predictive maintenance in the manufacturing process. And this figure actually shows a block diagram, the model showcasing the data flow among the different components of this solution. So in the next slide, I will explain it in details. So as I mentioned earlier, that this model is deployed on an edge platform and also on a fog platform. And this figure here actually shows the illustration of the deployment on the edge and on the fog platform. Here we can actually see that the image data are fed into the ML model. Actually, the model is deployed on the edge platform, specifically on a Y Atlas device, which my previous speakers, Lorenzo, already told about. And this model here predicts the anomalies on the incoming image streams, and from there the images are converted to JSON format for the seamless streaming to the cloud environment. And for the streaming, we use the Kafka. And in this case as well, our model, which is deployed on the cloud or the platform, it performs the anomaly prediction, and it actually generates or predicts the similar anomaly prediction score as on the edge device. And we have also developed an user interface for visualizing the identification of such anomalies, and basically facilitates an easy interpretation and decision making. The software and integration components integrated in this pilot 3 for this solution actually relates to both building block 6 and 8, as we can actually see on this illustration of this figure, here this ML solution for the fog is identifies as software 101, and for the edge it is identified as software 100. Now we will see here a demo which actually showcases our model's prediction output on the fog environment. It is actually implemented in Python GUI, and I will start the video on the left. So here the green dot it means that the images do not have any anomaly, and the red dots means that it contains some form of anomalies. And on the right video clips, you can actually see that the results on the edge and on the devices or the platforms are same, and it also checks that if that image contains an anomaly or not. So you will soon have a look at the results on the screen, that it shows that okay, the fog and edge results are same. The results is true, so it means that it doesn't have any anomaly, and if the result string is false, then it means that just the anomaly. Now let's go to the next slide. It's still playing here. Let's stop it. Okay, now I'll talk about the adaptability of our technology in the management machine sector. So our technology, which we developed through this ML model, so it actually generates a significant strides towards achieving the predictive maintenance in the manufacturing through vision data analysis, and it shows a quite good performance for the bottle packaging processes. So this model's ability can be actually adapted to other industry, such as the semiconductor industry, in which detecting the anomaly is really important. And in this case, this model can be adapted to actually detect the effective chips in the chip manufacturing process. Now I actually present a few notes on the future of our technology. So the unique selling point of our technology is that it can be seamlessly integrated into an existing manufacturing process, and we can use that transfer learning and multimodal fusion, and also many specific training methods to use this model in another manufacturing process, or which could be beyond the scope of Imoco's scope. And he can actually implement this technology in similar manufacturing processes, which can benefit from such a predictive maintenance. With that, I close my talk.
Thank you very much, Tarkil. And this concludes our webinar on the pilot 3 of the project Imoco for E. And if you want to know more, please follow us in our socials and visit our website at www.imoco4e.eu. Thank you again.